Hello, madam.
Hello, good
Uh,
afternoon.
Good afternoon. This is clear. Pujita, you are available?
Yes, sir.
Sorry, what?
Yeah. So I'm calling Pujita. One
Yes,
person
sir.
has to join.
Okay.
So you start the session. We are going to record this session. I
Yeah,
think
sure.
Pujita is available today. I think electrostatic part of Pujita required. So please help her.
Okay, yeah. So, can you make me a co-host so that I can share the screen?
Yeah, sure. Yes, I have made a post.
Okay. So my screen is visible, right?
Yeah, yeah.
Okay. So we shall be seeing the electrostatic solver today, especially parallel plate capacitor. So that is what was being asked for, right? So first of all, you know this GUI, right? I'm going to take a new design with an electrostatic solver. So for that, I'm going to take it from the desktop tab. Here you can see the desktop tab, and I'm going to insert a new Maxwell 2. Sorry, it should be a 3D design, right? I need a 3D design. So I'm going to take Maxwell 3D design from here, and this will get inserted into a new project. And the project already had, I had one project which I have been going through these days. So I've created a new 3D design here. You can see the 3D design which was formed just now. So by default, the solver type will be magnetostatic, as you can see in the brackets, right? So currently for parallel plate capacitor, and if you're interested in electric field calculation, you need to change the solver type to electrostatic. So I hope from these days you might be knowing how to take that solver type. So what we have to do is we have to go to this menu bar. There is Maxwell 3D solution type, and you can go to electrostatic solver from the electric set. Here you can see the solver sets in the electric set, and these are the solver sets in the magnetic set. Okay, I'm going to take this electrostatic solver and click OK. Okay, so the solver type has been changed here. So here you can see the difference between this 3D and 2D solver. Here for 2D we had in brackets the solver type, as well as we had this geometry plane option, because in 3D we don't need that because it already has this global x, y and z axis. So we don't have these two types like x, y or about z axis. So it's just the solver type which is available in the brackets. Okay, so this is the solver type, and we have to move in this fashion from the project manager, starting from boundaries, excitation. So for that, before that, we need to have a geometry, right? So some basic CAD features are available, as I have already told. So you can see the 3D geometries and 2D geometries and also line primitives here. So you can choose the whichever geometry that you need. Say for a parallel plate capacitor, I'm going to take a new box, okay, or a square or rectangle, whatever it is, a cuboid. Okay, I'm going to take this box, draw box, and I'm going to start it from the origin, 0 0. Here you can see one thing. Once you place a cursor in some of the any coordinates, you can see in the this bar, you can see the coordinates, right? X, y and z coordinates. So whenever I'm placing this cursor at the origin, you can see x, y, z coordinates at 0 0 0, right? So if you want to change any coordinates, like if you don't want to start from the origin, you can press tab from the keyboard and you can shift that. I'll show you. If I press the tab, you can see the x coordinate has been highlighted. So you can change that xyz coordinates by pressing tab. So this is one of the shortcuts you can use if you are making any geometry by your hand, as like this. So currently I'm going to start from the origin as such. So this is one method I'm just telling how you can use these coordinates to make a geometry. Okay, so I'm going to start from origin, and I'm going to place this opposite vertex somewhere, and I'm going to have a z axis like this, and I've created a box like this. Okay. From now, I think you will be familiar with the tool now, how you are going to draw this geometry and all. So just to make this box, I have just selected one vertex. The other vertex I have clicked once, and I have just dragged it in the Z direction so that a box is formed like this. Okay. So whenever a box is formed or whatever geometry is made in this GUI, it will appear in this history tree. You can see the box one, which was just now created. Okay. So you can edit the dimensions of this one or whatever geometry you have made in this GUI from the history tree as we were seeing for last 2 days. So to edit the dimensions, you can just double click on this create box. Okay. Under box one, there is create box. Double click on this box, and you can see the position, x size, y size, and z size. Okay. So this will correspond to what should be the x value, y value, and z value. Right. So I have already started from the origin. So position is the first vertex is at origin 0, 0, 0. Right. And say if I need a an area, or if the length and breadth of this parallel plate capacitor, I'm going to take as 25 mm by 25 mm, and a height of, let's say, 2 mm. I can change this x size, y size, and z size respectively. Okay. So x size should be 25 if I'm going to take 25 by 25. Okay. And y size should also be 25 because this is the xy plane, right? Xy plane. So this side the length is taken as 25 mm. This side also length is taken as 25 mm, and this height I'm going to take it as, say, 2 mm, right? So the dimensions of this box has been set here. So click apply and click OK. So now it has extended to a large scale. So I can fit it to screen to show how the box looks like. Okay, so this is one of the parallel plates of this capacitor. So we need one more plane. Before that, I need a dielectric or a space between these two parallel plates. So I'm going to draw a new box to represent a gap between the two parallel plates, right? So for that, going to take a new box again, new box. So if you have any doubts in between, you can ask, okay, so that I can stop and I can explain it, right? So I'm going to take a new box and starting from one vertex, and I'm going to place it in this vertex. Okay. And just drag it in the positive z direction. So a new box has been formed, and you can see it as box 2, right? And I'm going to change this dimension. Say if we want the gap of, say, 1 mm, I can uh, change the z size to 1 mm. Okay, this gap has been changed to 1 mm. Click apply. So we have two boxes now. One represents one of the parallel plates. The other represents the gap between two parallel plates, right? So we need one more box representing the other parallel plate. So the same way we have proceeded, I am going to take a box, draw from one vertex, the other vertex, drag it to positive z, and edit the dimension 25 by 25 and 2 mm in the z direction. Click apply. You can fit it to screen, fit all the toolbox. Okay, toolbar. So what we have is now two parallel plates. Two parallel plates and a gap in between. So if you want, you can rename this boxes. So currently, I'm not going to rename. If I want you to show how to rename, I can show that. You can just double click on this box and you can just uh, rename it as, say, bottom plate or whatever bottom plate. Okay. Only thing is that I think the gap should not be there in the naming. You can use an underscore as such so that the name can be written like this. If you want a gap in between, you can take it as underscore. While naming, a gap should not be there between two words. As you can see, you cannot write bottom space plate. You'll have to write bottom underscore plate, underscore, or whatever sign or symbol, or you can just you don't if you don't need any space, you can just combine these two words as such. It's all up to you how to proceed. Okay, apply. Okay. So this was box 2. Oh, so this is the gap, right? Or the dielectric. Even though I'm going to take vacuum as the dielectric, uh, I'm just renaming it as dielectric, and the box 3 as upper plate. Okay. So the geometry has now been formed. What we need to do is we need to change this material to a perfect conductor for these two plates. So we can select these two plates, bottom and upper plate. So you can press Control to select both from the keyboard, and you can select both the plates, bottom and upper plate, and you can place your cursor in somewhere either on the bottom plate or upper plate and right click, and there is assign material option, assign material. So this material library list will appear and you can choose a perfect conductor from it. So you can search by name as PEC. PEC represents the perfect conductor. Okay, there is one more perfect conductor here. The values or the properties remains the same. You can choose this PEC representing the perfect conductor. Okay, so you can see that the two plates, the upper plate and bottom plate, has been changed from vacuum material, which is the default material here. Okay, it has been changed to PEC, the perfect conductor material, under perfect conductor material, right? And this dielectric, I'm going to take the vacuum material as such, representing the vacuum, right? So the geometry part is now over. And for 3D, to represent, you don't have to use a boundary condition, uh, because it is already a 3D geometry, right? So you don't need a boundary condition here, unless if you have to, if your flex is going, say you need to have an insulating boundary between some conductor or some area which is going to conduct. So in that condition you can have an insulating boundary as such, but other than that, usually in 2D we used to give a boundary condition in the regions, right? It is not needed in this 3D design, so we can skip that. And excitation, we can start giving for these two plates. Say I'm going to give a 0 voltage for this bottom plate. So I'm going to select one of the plates, and you can just right click on the GUI, and there is assign excitation here, and you can choose voltage excitation with a 0 volt value. You can choose the unit from here. Zero, anyway it is millivolt or volt, doesn't matter. So value you can give it as 0 and click OK. So when you have inserted or assigned an excitation to any of the geometry, it will appear in this project manager under excitation. As you can see, for voltage it has been assigned to the bottom plate, right? So similar way, we have to assign another excitation for the upper plate, so that there is an electric field between both plates, right? So I'm going to select the upper plate, and you can right click and give the excitation. So assign excitation voltage, and you can give say 1 volt to the upper plate. Click OK. So voltage 2 also has been added, which is assigned from the upper plate, right? So both excitation is now over. We can just now add an analysis setup, right? So right click on analysis, and there is add solution setup. So these are the criteria or the properties that we are going to take in the static solvers. So we have seen this in the magnetostatic solver. So the similar way the properties remain same for the electrostatic solver also. So these are for applicable only for static solvers. Okay. So we have to specify what is the maximum number of passes, right? So say if the percentage error is small, we can go for say default 10 value, 10 maximum number of passes. So I'm going to reduce the percentage error to say 0.1 percentage. You can reduce even further like 0.01 or 0.001 percentage. As much as accuracy you want, you can reduce the percentage error, but you cannot reduce it to very small value because it is going to take a lot of time to converge. So currently I'm going to take 0.1 percentage with the maximum number of passes as 10. And in convergence criteria, we have given, let it be the default value. So refinement per pass has been given to be, say, 30% refinement, which means after each pass, it will be 30% refined. I hope you understood it, the clear sense. So we have the tetrahedra as the mesh components, right? So after one pass, it will be refined 30% from the previous tetrahedras, how it has been. So after that, minimum number of passes has been given to be one. Even though it gets converged in the first pass, at least there should be two minimum passes, right? And minimum converged passes one. After the convergence, there should be one more pass, right? So this is the criteria that has been given in the setup. So once the analysis setup has been formed, we can directly go for analysis.
Excuse
So
me,
before
ma'am.
that, yes,
What does pass mean?
I'll show you after the analysis. I'll show you in the
Okay, okay.
convergence how it is. Um, so before the analysis, I'll just validate if the model is right. You can press the simulation tab here, simulation tab, and there is validate option. Validate. Okay. So once you validate, if everything is green tick mark, you can directly go for analysis, right? So here everything is fine. If there is any warning or error, it will appear in this message manager. Okay. So since it is all fine, you can directly go for analysis. You can right click on the setup and directly go for analyze. So you can see the analysis progress in the progress window. It has not started. Let it start. You can say the adaptive pass one, two, right, that like that, right? So that is the pass means. So I'll show you how the convergence is. You can right click on the setup one, and there is convergence option here. Okay, that setup convergence. So you can see the tetrahedra how it is. So it needed only two passes. So in the first pass itself, it got converged. So the target we have given was 0.1 percentage delta error. It has already having the energy error of less than e raised to minus 28 power. So the tetrahedra needed, or the mesh size needed, mesh elements needed, is only 30. So we have given the criteria to be having, even though it gets converged in the first pass, we need at least two passes, right? So this is the pass meaning. Means even if we are going to increase the percentage error, how much does the mesh increase per pass? Hope you understood.
You mean tetrahedral mean 30, 41? What is this mesh size? Number of mesh particles
Yeah,
is it?
mesh elements, correct, correct.
Okay, okay, ma'am. Thank you.
Okay. Yeah, so for this condition, this is how it goes. And now the question comes is how to find the capacitance of this one. Okay. So we have given a basic analysis. We have had the basic analysis. So I'm going to just plot the electric field of how it will be. So you can press Control A to select all. Okay. Control A. And you can right click on the GUI. There is fields option. Fields. E, and you can see go for E vector, how the vector plot goes for an electric field. You can see the electric field is going from the upper plate to the lower plate, because this has been given the voltage 1 volt, and this has been given the ground voltage 0. So the electric field direction is from upper plate to bottom plate. So you can see that, see the direction. You can rotate it and see how it goes, right? So this is how the electric field looks like for this condition. Actually, this is a very ideal condition. In practical case, this is not the case. I'll show you that too. So if you want to have a transparency, you can right click, you can select the whole geometry. You can press Control A, and in the properties window, you can see the transparency here. Okay. So basically by default, it will be 0. Default value, it is opaque. So you can increase the transparency rate so that you can see the electric field lines a little bit more clearly. Okay. So this is how the electric field vector looks like. Now the question arises to how to find the capacitance of this parallel plate capacitor. So to get the capacitance value, we have to assign matrix for that, right? So in the same way, we used to include the matrix in the magnetostatic solver for finding the inductance. Similar way, in electrostatic, we have to include the matrix again for finding the capacitance. Fine. So you can right click on the parameter here in the project manager. Okay. In the project manager, there is parameter, right click, and there is assign matrix option, matrix, and you can include both the excitation, the voltage excitation for both upper plate and lower plate, and click OK. And you can directly go for analysis again. So this cannot be, even though you have added the parameter after the analysis, that will not reflect the capacitance value here. So one, if you have created or if you have assigned the parameter after the analysis, you will have to reanalyze it to get the capacitance value. Okay. So since we have analyzed and we have added the parameter after this, we are going to reanalyze it. So right click on the setup and go for analyze. So before that, just revert to initial mesh and click yes. Okay, so that the earlier solutions will not affect the new solution. So it has been reverted to initial mesh. Go for analyze. Hope you are able to follow what I am saying, right?
Yes, ma'am. Go ahead.
Yeah, thanks. Okay, so once the simulation is over, normal completion of simulation appears in the message manager. So you can right click on the setup again to view the capacitance value. Right click on setup and there is solutions. So in the solutions, these are the tabs that we can start with. From the profile, you can see how much time it took for the analysis. So it just took fraction of seconds. The total time it was taken to be 0. Uh, and the convergence, you can see it has only 41 elements here. And forces, we have not assigned any force, and torque also is not applicable here. And coming to the matrix, you can see the capacitance value and the unit is in picofarad. So it is coming to be 5.53, which is approximately similar to the analytical value here. So we can see what is the analytical value. So you know the capacitance value of a parallel plate capacitor, right? Analytically, how to calculate the capacitance value. So what was the equation? Cal- The capacitance is epsilon 0 A by D, right? Epsilon 0 A by D epsilon 0 is 8.854, right? Epsilon 0 A by D, and it is 8.854 into 10 raised to minus 12. So 8.854 into A by D. A is the area of the parallel plate, right? Area we have taken to be 25 by 25 mm. So 8.85. You can also calculate in between. If you get a result faster, you can just tell me what the result is. 25 by 25 was the area, divided by the gap has been taken to be 2 mm, right? Sorry, 1 mm gap has been taken, so divide by 1. So it is approximately 5333. So this into 10 raised to some power. So power 10 raised to minus 12 represents the epsilon 0, and the other one will be 10 raised to minus 6 and divided by 10 raised to minus 3, 10 raised to minus 15, which equals 5.53 into 10 raised to minus 12. So this is the exact value here, right? 5.53 picofarad into 10 raised to minus 12 farad. Hope you understood how to calculate the capacitance, right? So this represents very ideal value of capacitance for a parallel plate capacitor. So in practical case, there will be deviation with respect to capacitance when you consider a region around it, because in ideal case, there will be some kind of fringing that is going to happen in between the two parallel plates. So this is a very ideal condition. So to represent that condition, parallel practical case, even though we don't have a practical formula for that, this is the idealistic or analytical formula for calculating the capacitance. In practical case, how it will be, I'll show you. Hope you are clear till now.
Yes, yes.
Okay. So I'm going to copy the same design. So you can just right click on the design, copy, and paste it in the same project. Okay. Did I copy another design? Yeah. So this has to be copied, the ready design. Right click on the project, paste, and you have another 3D design here with the same parallel place, same geometry. Okay, I'm going to show you how it is going to affect if you have the a region around it, if you have the air that has been considered around the parallel plates. Okay, so you have to for that you have to create a region around this parallel plates or the geometry. So there is a region, as you can see in the toolbar. There is a region. You can you can just click on that region, or if you can't find it in the toolbar, there will be it will be in the menu bar, draw, and there is region here, region. Okay, and you'll have to enter the percentage offset of that. If you are going for 100 percentage offset, click OK. So you can see a region that has been formed around the geometry, right? So this is the region around the geometry, and by default it will be under vacuum. So we are going to consider this region. So for time being, I'm just going to hide this region, even though the region is still there in the analysis. Okay, so region has been added, and we can directly go for analyze without changing the settings, and we can see if this pass is sufficient for that to converge to 0.1 percentage. So right click on the setup, go for analyze. So only difference that we have done here is we have just created a region around this geometry, and we are going to analyze then and you can see the capacitance value, how it is going to affect the capacitance, right? So the simulation is now over, but you can see in the message manager that the adaptive passes did not converge based on specified criteria. So it has not converged here. So it has to converge for getting the accurate results. So you can just increase the number of passes so that it has enough time to converge, so that the energy error or the delta error, it comes down to 0.1 percentage. Okay, so you can just try to increase the number of passes. I'm going to make it to 30 passes and click OK, and going to reanalyze it. Now the energy error is at 0.8 percentage, so it has to come down to 0.1 percentage for it to converge. So you can see at each pass the number of tetrahedron, number of elements is increasing with 30% refinement per pass. Okay, so it's now 16th pass. Let's say at what pass that will converge. Now it has reached to 0.3 percentage. So here you might have noticed that we have not given any mesh operation here. So it is automatically meshing. So this is one of the best feature that Ansys Maxwell offers in static solvers, basically for magnetostatic solver also and electric solver, and eddy current solver also. There is this is applicable, but for transient solver and AC condition and DC conditions is not applicable. DC condition I'm not sure about if it is applicable, but other three solvers it is not applicable anyway. We have to manually mesh for that. So in this condition it will automatically see where the energy density or the energy error is more, and it will fine tune the mesh at those areas where we have to have the real focus on, right? So that is the adaptive meshing technology which has been applied. So it has now turned to 0.13 percentage, and it will converge maybe in the next step. Not in converge in the next step, but there it has gone to adaptive pass 26. Maybe it will converge in the 26th pass if it goes beyond 0.1 percentage. Okay, it has come down to 0.1 percentage. Okay, so I had memory issues, so it got the error. Let me see if it has produced a solution. No. Okay. Now the simulation has been completed. So we can see what is the capacitance value. So you can see there is a change in the capacitance value. The other one, without the region being considered, it was approximately 5.5, right? So 5.5 picofarad, and now it has changed to 6.5 picofarad. Okay, so this is where the difference comes up. This is almost close to the practical value, how it will be considering the fringing. So I'll show you how the electromagnetic field looks like in both the cases. So first one, without considering the region, I'll show you how it is. So we can start plotting the electromagnetic, the magnitude of electric field in any of the planes. So I am going to select a plane, say global YZ or XZ. So we can plot on both planes. So I'm going to plot on XZ first. So choose that plane, XZ. Okay. And right click on the GUI. There is fields option and there is E. We have gone for E vector first. So I'm going to take magnitude of E now. Okay. So this is the value of E field for this condition without considering the region here. Fine. So this is like it has E field only in the uh, on the in this gap. It has not considered anything outside that because we have only this geometry present here. Similar way, we can plot for the visor plane also. You can select that plane and you can again go for plotting fields E, Mac E, and click done. So the same the the E field plot, it is similar for both Z plane and XZ plane. So this is how it looks like ideal condition for finding the magnitude of electric field for parallel plate without considering the region. So let us see what happens if we have considered the region, how the magnetic magnitude of E field looks like. So this was the next design considering the region outside the parallel plate capacitor. So I'm going to choose the plane here, any plane, not XY. It should be XZ. Okay, XZ. Right click, fields, and magnitude of E field. Done. So let me zoom it, or I'll just rotate. I'll plot in the other two. Field E, magnitude of E. So you can see a fringing here that is happening on both the edges. Okay, so that is the that is more representing the practical case for a capacitor. Here you can see that fringing effect. Hope you are able to see it. Okay. So there's the basic difference if you are considering the region around this parallel plate. So this is the more realistic way of analyzing a parallel plate capacitor. So you first draw a geometry, you create a region around it, and you start analyzing with electrostatic solver, and you can find the capacitance which is more closely to the practical value. So hope it's clear. So what else do you want from this one? There was one more question, right? Some,
Modeling the motion of an object.
yeah, objects motion supported. So in this case, it's actually a static solver. We cannot create a motion as such. We can have a variable. We can use a step-by-step motion. Means it's not a continuous motion. We will be setting it as the move vector as a variable. I'll show you how we can do that. But I'm just trying to. I'll copy the design and paste it. So I'll just hide this region and fit it to screen. So you want the motion of any of the places, eh? Is it like that?
You can insert another object maybe near to it.
Okay.
Maybe a dielectric you can put similar size, maybe plate. So I just want to see how the field is getting affected.
Okay. Okay, I'll change this one then.
Yeah.
Dielectric 2.
Or you can put next to it. Maybe you keep it as it is. Put
Okay.
another object next to it. How means I'll just show it to you. Just a second.
I'll stop sharing. You can share and show me.
No problem. You can share. I will annotate there only.
Okay.
I was trying to connect my. You can share, madam. I'll just annotate there.
Yeah.
Yeah. So what I'm saying is maybe something like this. Okay. So can I have maybe this to be a maybe water body?
Okay.
And I would like to see how the field lines will get disrupted and how would the capacitance value change.
Okay, I'll place a new object here.
Huh.
Okay. I'll take another box and okay.
Maybe a bigger object is fine. Yeah.
So
So
this is
maybe you
how
can still increase it in Z direction maybe so that it
same size.
same similar
Same size. So it will be
5,
5
yeah.
mm. Okay.
So can you make it dielectric of water 80? Water is 80.
Yeah, you just tell me the property.
Uh, Water 81. Yeah.
This is fine.
Yeah. Fine.
Okay. So let me see the region. Okay.
So the voltage can we apply as 0 volts? I would like to ground that object.
Okay. Yeah, that is possible. You can assign the excitation voltage 0 volt. Okay. Click OK. So whatever excitation has been given here, it will appear under this excitation. Okay.
Okay.
So I'll start analyzing again.
Yes.
It is also going to take a little bit more time for that.
Okay.
Since I'm having memory issue, I don't know if it gets complete. But
Maybe you can increase or decrease the accuracy to 0.5% maybe. I think around 0.2% you could solve it. I think if I could see clearly.
Yeah. Of time being, shall I change it to 1%?
Yeah, 1% also you can change, no problem. So before you solve for that 1%, without that object and with object, I think we required, right?
Yeah.
For me to compare.
But that accuracy will be different. But let us see how the difference
Yes.
is.
So previously you have created that
Yeah, I
file.
have. Correct. So I'll just change the setup from 0.1 to 1% and I'll reanalyze it. So in this case, before reanalyzing, you need to revert to initial mesh, or else it starts from the meshing. It has been there in the last mesh. Start from the last mesh. It will start.
Okay. So then basically would it be advantageous because it was not able to solve that? Will it not require more data? It may not require more data points, right? or
No.
am I wrong?
But you will be realizing if you have changed something, right?
Okay.
But that change will not be affected here if it is starting from the last point where it has stopped.
Okay.
So to revert that or to know that change, you will have to revert to initial mesh uh, to
Okay.
know that difference and to
Okay.
incorporate that change.
Sure.
Okay.
Hmm.
So sorry. 7.2.
Okay. Usually, whenever we solve, we will usually find out charge, right? And then since the voltage is fixed, so the capacitance we calculate as C equivalent to QV. But you are showing a
Charge
bit differently.
charge also is available, sir, but I have not used it now.
Okay.
But
Okay.
you can try it out.
Sure.
Same way. Right click, assign excitation. There is charge option here. Okay.
Okay. Okay. No, so you are saying that the voltage itself is being changed to reflect the value of the capacitance, huh?
Yeah, yeah.
Okay. So what is this export solution next to this?
Which one?
One second.
You can export it to any CS,
Okay.
Excel file or XYZ data.
That is basically that voltage values is being exported.
Yeah. This is actually the capacitance value.
Hmm.
So
Okay.
type capacitance and the units is here. So
Okay.
here we have not included that voltage which you have assigned for 0 volt here. So
Hmm.
if that was also there, that mutual capacitance also could be same, how it could be. The same way we have included the voltage here, right?
Uh-huh.
So right click on excitation, assign matrix. So sorry, yeah, site excitation. Where was that matrix? Sorry. Not an excitation parameter. Under parameter, assign matrix. We have included.
I think you have not included anything. I think we have to include
Actually,
and solve.
one and yeah, yes, I think some we have included these two only. We have not included the other one. Okay. So
Okay.
if you want to have the mutual capacitance between these, you can include that too.
Can you
So
show?
that
Is it fine? Quickly, can you show it?
yeah, no problem.
Yeah.
This is but this when you say beta break versus beta total, both are same. That is one, including the sign of all the elements, right? Including sign.
So I actually did not get, I mean, how we are saying that the C1 is equivalent to V1, or because there are different voltages. Like previously you got the same value for others, all the values, but
Dipole moment cannot be negative.
Yeah, we
Polarizability cannot be negative.
once you have the mutual capacitance, how do you take? I mean, maybe I think here it will be much clearer. I think once you include it.
hmm.
Yeah, molecular dipole will be along that CO vector, right? You are having mu j, and that's why. Then if that is the case, then beta H and beta Z is same for your molecule. Yeah, that's in that slide itself written also. No. We need to take this sign actually. Need to definitely take this sign. We cannot just take the magnitude. They're all components, no? Because the components of different. So components will have positive or negative sign. Yeah. Can I see the mu x and mu y? They are zero. Yeah, you have got for the calculation you have got zero, right? Yeah, your calculation is perfect, right? So basically, you consider all the signs.
Okay.
You see, these are all tensor quantities, and when you are calculating the component,
Voltage 3 is 436.4.
you consider the sign. So even if the values are 0.5, that's fine.
Okay, so how do you say between C12 is minus 6.4? Huh?
Yeah.
Okay. So what is 1 second? So what is this one and what is this one?
No, this is like C11 for
Okay,
this
this is
one.
C11. Okay.
C12, C13, and this will be C21, C22, and C23, like that.
Okay. Okay. So this is the self capacitance. Huh? How?
Yeah, it will be
Okay, and the other ones are mutual
diagonal
capacitance. Okay.
mutual capacitance. Yes.
So I think this is mentioned in the sheet, or I mean a main sheet.
Which sheet?
How to solve? I mean, like you'll have some sheets, right? Solver, how to solve. So how do you?
Yeah, it is like that.
It is mentioned. Okay.
It is mentioned. Yes.
Okay. Okay.
If you
So
have any doubts regarding a particular subject, you can go to help. Okay, help.
okay.
There is a Maxwell help file here. Okay,
Okay.
and it will be okay. So this, which version do you have in your hand?
Dwarka, which version we have?
It's 2020 R2
21.
maybe.
Okay.
21 R1. Okay, similar way it will be like that. In 2021 R1, it will not directly go to this browser. It will have a PDF of its own. Since
Okay.
I'm using older version, it is going to this one, and
Okay.
there is Maxwell PDF available here. Maxwell help is there.
Sure.
Okay,
I'll
and
look
you
it.
can for any particular topic like capacitance or any solver, you can just press Control F to find that, and all the details available for that particular topic will be shown from that.
Okay.
Okay.
Yeah. So changing the environment is basically what you said is to put that region, correct?
Correct.
So can I have two different regions for the capacitor and this one? Environments may be different.
No, that is not possible.
Not possible. Okay. The temperature can I change?
No, temperature here we cannot change because we don't have that access to that.
Okay.
So we can have a multiphysics coupling with this one. So if you have workbench, you can have that static solver. Sorry,
Okay.
some mechanical tools like structurer or CFD, whatever it is, and
Okay.
you can have a coupling.
Okay. I have to couple it. Okay.
Yeah.
Okay, so thank you. So Pujita, any questions?
Anyway, if he wants, he will tell you. Okay. Otherwise,
Say if you want any motion like this, I'll tell that too.
Uh-huh.
Say if you want to place this object somewhere around the z axis, like if you want to move it up or down,
Hmm.
in static solver, basically that motion is not possible, but we can create it as a variable.
Hmm.
Okay, so in this case,
You
we
just
can
move it to
just
next point. Okay.
you can say you can just right click on that object and there is arrange option, edit, arrange, move.
Okay.
Okay,
Okay.
and you can just set a reference point, say the global coordinate origin
Okay. Okay.
0 0. You can just double click on that and you can see a new what to say, a new object has been formed, or a new, what to say, function has been formed, like move option
Okay.
has been
Okay.
formed. So
Mm-hmm.
double click on that. Move vector is at 0 0 0. That means it has not moved now.
Okay.
So to move it in z direction or any coordinate, you can just make, instead of a zero value, you can
Mm-hmm.
make it as a variable.
Mm-hmm.
Like say you want to move it in the z direction, you can choose a variable here. Say
Mm-hmm.
writing a name instead of a value. Okay, I'm
Okay.
just writing in the z direction move option, and
Mm-hmm.
if you press enter, it will ask for what is this move.
Okay.
Okay, so it has to be represented in coordinates, like, so the unit type has to be in length. Okay, in unit mm, and
Mm-hmm.
value we can keep the default
Okay.
value 0 and click ok. Okay,
Okay.
and now there is option to have optometrics here. Optometrics, you can right click on optometrics, add parametric, and you can add that variable move starting from 0 to say 5 mm in steps of 1 mm, say, and press add.
Okay.
Okay, and in table you can see what are variables that we have given for that particular name variable move. Okay, and you can just in the options tab you can check the save fields and mesh for each step and click ok. So if you are trying to have that move option, say, and you can directly this parametric setup has been added, you can right click on this setup and you can solve that. Okay, it will show the results for each of that step.
Mm-hmm.
I'm not going to do that
Sure.
correct.
Sure. Okay. Fine. Mm.
Say if you are having this move vector 2 mm, you can see the object has been moved. Okay,
Okay.
so once analysis over, you can see the variation with respect to each of the step. So that is how you can utilize this optometrics option.
Okay.
Okay, so hope it is clear. So anybody has any questions, or we shall wind up?
not like keep on increasing.
I think okay. Pujita, any questions?
So right now we are having
No, sir. It's clear for me.
Okay. Okay.
Thank
Fine.
you. Thank you.
Thanks. Okay, you can try it out, and if there is any doubt, you can mail
Uh,
us at lf.support at
one more small question. So
Yeah.
you were talking. I mean, let's say this is the whatever that upper electrode.
Huh.
Okay. On just draw it. Small dot only.
Yeah.
So let's say here I want to make it as one thing, and between them I'll have to place. Okay. So the boundary you are talking about, right? Which I cannot set here in 3D.
Hmm.
So if I want an insulated body, how do I do that? I will have to create one more object. Huh?
One more object, yes.
Okay.
Can we create two regions, madam?
No, two regions is not possible, only one region. Why
Okay.
do you want to create a two region?
I just wanted to know whether it is possible or not.
Okay.
So I mean, like,
Okay.
let us say I
No,
enclose something.
actually, I asked if I needed to learn if there is any. That is why I asked.
Yeah, for
Okay.
example, let's say you have a, I mean, like I was asking, right, where a temperature effects can be modeled in a
Ah, okay.
region. So I wanted to see if that is in different temperatures. Uh, so just wanted to know whether it is possible or not. One more question. Let us say I want to apply a frequency-based excitation to this electrode. Is it possible? Voltage.
Frequency based excitation is not possible using electrostatic solver.
Okay.
You'll have to go for eddy current solver for frequency domain analysis. So
Mhm.
you will get but in that electric field will not be seen, but all the magnetic fields like that it will be seen with respect to frequency.
Okay, you cannot see electric fields. Okay.
No.
Okay. Thank you.
Okay, yeah,
Uh,
thanks. Okay, shall we
Thank
wind
you.
up now?
Yeah.
Okay.
Thank you very much.
Thank you for your time. Yeah.
Bye.
Bye.
Bye.